Voyager 1 is currently flying through a region of space that is 10 times emptier than anywhere in our galaxy should be. Scientists call it the local bubble, a vast cavity of almost nothing, about 1,000 light-years wide, carved out of the interstellar medium by a series of ancient stellar explosions. And here's what's strange. We're inside it too. The entire solar system has been drifting through this density hole for the last 5 million years. Voyager is just going deeper, and the data it's sending back from inside this void is changing what we thought we knew about the structure of our galactic neighborhood. Here's the full story. The local bubble, also called the local cavity, is not a theory or a model. It is a directly observed structure in the interstellar medium surrounding our solar system, confirmed through X-ray observations, ultraviolet absorption measurements, and three-dimensional dust maps of the nearby galaxy. It extends roughly 1,000 light-years in diameter, and inside it, the density of interstellar gas is about 0.05 atoms per cubic centimeter. The average density of the Milky Way's interstellar medium is roughly 10 times higher, around 0.5 atoms per cubic centimeter. So the local bubble is, by galactic standards, a genuine void. A pocket of space that is almost completely empty of the gas and dust that fills most of our galaxy. To put that in perspective, the best laboratory vacuum we can create on Earth, using cutting-edge equipment, still contains thousands of times more particles per cubic centimeter than the inside of the local bubble. The void Voyager is navigating is not just empty by human standards. It is empty by the standards of interstellar space itself. It is a hole within a hole. A region where even the already incredibly sparse gas between the stars has been swept away and replaced with something closer to absolute nothingness, an ultra-thin, million-degree plasma so rarefied that it barely registers at all. And the story of how it got that way is one of the most violent chapters in the recent history of our galactic neighborhood. Within the local bubble, the solar system is currently embedded in a smaller structure called the local interstellar cloud, a denser cloudlet about 30 light-years across, flowing through the bubble like a fog bank drifting through a vast empty warehouse. Voyager 1 crossed the boundary of our solar system's own protective bubble, the heliosphere, in 2012. Since then, it has been measuring the properties of the very local interstellar medium from inside the local interstellar cloud, at the edge of the larger local bubble. As it travels further, it will progressively move into regions of the bubble that are even emptier, regions that the cloud doesn't reach, where the full near vacuum of the local bubble's interior is exposed. That transition is what scientists are now beginning to observe in Voyager's density measurements. How does a region of space 1,000 light-years across become 10 times emptier than everything around it? The answer involves one of the most catastrophic and sustained periods of stellar death in the recent history of our galactic neighborhood. Approximately 14 million years ago, a cluster of massive stars in what is now the Scorpius-Centaurus stellar association, a group of young, hot stars about 500 light-years from Earth, began dying, not one at a time, in waves. Dozens, possibly hundreds of stars exploding as supernovae over millions of years, each detonation sending a shock wave of energy and gas expanding outward at thousands of kilometers per second. A 2022 study in the journal Nature, led by researchers at the Center for Astrophysics, Harvard and Smithsonian, was the first to produce a detailed model confirming that a chain of roughly 15 supernovae, firing in sequence over millions of years, generated the local bubble we live inside today. Each supernova contributed its energy to the expanding bubble, sweeping the surrounding interstellar gas outward like a snowplow, compressing it into a dense shell at the bubble's edge. Over millions of years, that shell thickened and collected. Today, the wall of the local bubble, the dense boundary between the void inside and the normal interstellar medium outside, is where almost all of the nearby star formation in the galaxy is happening. The molecular clouds in the Taurus, Perseus, and Ophiuchus regions, which we can observe as dark patches against the stars, are all sitting on the surface of the local bubble, compressed into star-forming density by the ancient shockwaves that created the void. The violence that emptied the space around us also, paradoxically, triggered the birth of new stars at its edges. Our void is ringed by stellar nurseries. And our solar system entered that void about 5 million years ago, walking, as one scientist put it, into the scene of a violent crime. Now let's talk about what Voyager 1's instruments are actually measuring as it moves through this environment, because the data is more nuanced and more interesting than the simple phrase, density hole, suggests. Since crossing the heliopause in 2012, Voyager's plasma wave system has been recording the electron density of the surrounding interstellar medium. The early measurements showed electron densities consistent with the outer edge of the local interstellar cloud, roughly 0.06 to 0.06 to 0.06 electrons per cubic centimeter. As Voyager moved further from the heliopause, the density data showed a rising gradient. The medium was getting denser as the spacecraft moved through the cloud and encountered material compressed by the heliosphere's own motion through space. But that rising trend was expected to peak and then begin to fall as Voyager eventually emerges from the local interstellar cloud and enters the emptier interior of the local bubble proper. Don Gurnett, the University of Iowa physicist, who led Voyager's plasma wave science team for decades, described his best guess for what comes next. The density will reach a peak, possibly from interstellar material, piling up near the heliopause like snow in front of a snowplow, and then it will come back down as Voyager moves into the emptier regions of the bubble. That prediction has not yet been confirmed by the data, but the trajectory of Voyager's measurements and the known structure of the local bubble from external observations suggests that the spacecraft is approaching a transition from the edge of the local cloud into a region significantly emptier than anything it has measured so far. That is the density hole the title of this video refers to. Not a void in the science fiction sense, a real, measurable, documented transition in the density of interstellar plasma that Voyager's instruments are, or were, before some were shut down, in a position to detect. What makes Voyager's position uniquely valuable for understanding the local bubble is that it is the only instrument humanity has ever placed inside interstellar space. Every other measurement we have of the local bubble comes from remote observations, absorbing starlight through the medium, detecting X-ray emission from the hot plasma, mapping dust at the bubble's edges. These are all indirect methods. Voyager is the first direct probe, and the continuous density map it has been building, originally through sporadic plasma oscillation events, and since 2017 through the persistent plasma hum that Stella Ocker detected in the plasma wave system data, is the first in-situ measurement of the interstellar medium's density structure over a significant stretch of the local bubble's interior. It covers about 10 astronomical units of interstellar space so far, a tiny fraction of the bubble's total extent, but a fraction that no prior observation could provide. And the data is showing something important. The interstellar medium is not uniform. It is not a smooth, well-mixed gas at constant density. It is turbulent. It has structure at scales of 1 astronomical unit and smaller, eddies and fluctuations and density variations that no telescope on Earth can resolve. Voyager is revealing, for the first time, what the inside of the local bubble actually feels like from the inside. Not what it looks like from outside. What it is. That is a fundamentally different kind of knowledge. And as the spacecraft progressively loses instruments, the cosmic ray subsystem was shut down in February 2025. With more to follow, the window for collecting that knowledge is narrowing. The density hole is real. The map being drawn is real. And the map maker is running out of time. Eventually, in timescales of millions of years, long after Voyager has gone silent, the solar system itself will exit the local bubble. The sun is moving through the galaxy at about 20 kilometers per second relative to the local interstellar medium, and its trajectory will eventually carry it through the bubble's wall and into denser interstellar gas on the other side. Astronomers believe that encounter won't happen for several million years at minimum, but when it does, the heliosphere, the protective bubble the sun maintains around its planets, will be compressed significantly by the higher outside pressure. Some models suggest that during such an encounter, galactic cosmic rays could penetrate the inner solar system more easily. Whether that would have any measurable effect on Earth is an open question, possibly even one that Voyager's density measurements, made from inside the bubble while it still operates, could help answer by giving us better data on what the transition region actually looks like. Voyager 1 didn't set out to map the local bubble. It was aimed at Jupiter and Saturn, nearly 50 years ago, by engineers who couldn't have known what lay beyond the heliosphere. But that's the nature of exploration. You go as far as you can, you measure what you find, and you discover that the map you thought you had was incomplete in ways you couldn't have imagined. The density hole is real. It's enormous. We live inside it. And right now, a 47-year-old spacecraft, still transmitting, still listening, still measuring, is slowly drawing us a picture of its interior, from the only perspective that matters, from within. If this episode changed how you see the space around us, subscribe and drop a comment. And if you want to go deeper on the density measurements Voyager has been making since 2017, the persistent plasma hum and what it reveals, we covered that in full detail in a previous episode. Link in the description. See you in the next one.